Okay, today we're going to talk about Euler's method, which is 9.2, day 1. There's 2 parts to 9.2. Okay, first what we want to do is we want to recall linear approximation, which came from the tangent line formula to f of x at a, comma, f of a. So at that point, right? So if you remember our tangent line approximation, it was f of x is approximately equal to f of a plus f prime of a, x minus a. Remember, x minus a is the same thing as a delta x or a dx. Okay, so they're the same thing. Okay, so we are going to change this to Euler's method by relating it to this. First, let's talk about how this is going to be used. So let's say you have a point, a comma f of a. We're going to say it's right here. And you have some function, okay? We don't know what the function looks like. But if we use this linear tangent approximation, let's say that we have this tangent line that goes in this direction. So if we were to plot a point here at a comma f of a, and we followed this tangent line, it would be taking us in this direction. Okay, which now lands us at our next point, B. Okay, so here we have B, comma, f of B. All right, and let's suppose we have a new tangent line approximation, which now takes us in this direction. And if we follow this tangent line, there is our C. And this is going to be C, comma, f of C. So what we're doing is we're using our tangent line at this point of tangency to help us approximate another point on the curve of f of x, supposing we don't know exactly what the curve of f of x is. Then once we get to a new point, then we're going to use its tangent line to help us approximate another point on this curve. Okay? And this is all because we don't know what the actual curve is, but we do have enough information. We do have the derivative, and we do have the point of tangency. Okay, so this is used to approximate points on the curve of f of x. Okay, that's what linear approximation is. So now what we're going to do is we're going to relate this to Euler's method. Euler's method is essentially the same thing as linear approximation. We're just going to use a little different notation, okay? So let's say I want to find out a point, okay? Now, instead of saying, if I want to find out f of x, I can say, well, it is approximately equal to. Now, here, this function is dependent on x. So I am going to write f of a, or let me say actually f of x naught. I'm going to say f of xn. Plus, now this is the derivative, and this derivative, the ones that we're used to using, are dependent on x. But now we're doing differential equations, which can also be dependent on x and y, which can be dependent on just x, or it can be dependent on just y. So I'm going to write this as f prime of xn, comma, yn, derivative that is dependent on both variables, or it could be of just this, or it could be of just y. Okay? This is going to be used to approximate f of xn plus 1, the next point. Okay? And this, we said, is like our delta x, right? Which is also like our dx. Now, when we're using Euler's method, they like to use the term step size, which they note as h. Okay, so h is essentially the same thing as those. So I'm going to multiply it by h, h, h. So these are all the different forms of Euler's method that you can use depending on the differential equation that they give you. Okay, so let's look at our first example. Here's our first example. You're going to need a calculator, so you might want to pause every once in a while. Okay, so we're applying differential equations to Euler's method. So our first example says, given dy dx is equal to x squared plus y, and you're also given this initial point, use Euler's method to approximate this using step size of this. Okay, so this is the initial point. This is essentially the same thing as our f of a. Okay, so our point that we're given here in this situation is 1, 2. That is our first point that we're given. Okay, this right here is the same as our derivative, and if you notice that it's in terms of x and y, so this is going to be f prime of x comma y, a function of x and y. Okay, so now what I'm going to do is I'm going to first write down the point that I'm using here. I'm using 1, 2. Okay, and I'm going to write down Euler's method, which is going to be f of xn plus f prime of xn comma yn times your step size times h. So what is it going to be for this situation? Well, f of xn, that is going to be 2. Okay, or let me write it like this: f of 1 plus f prime of 1, 2. And what is our h? 0.1. So I'm just going to do baby steps. So what is f of 1? F of 1 is 2 plus. Now what is this? This right here is us applying this formula right here. Okay, so I'm going to put 1 in for x and 2 in for y. So I'm going to have 1 squared plus 2. And all that multiplied by 0.1. And that should generate my new point. So if I go to my calculator, I can enter this in, which I'm going to be using this formula often. So I am just going to actually enter it in like this. I'm going to call this my y plus x squared plus y times 0.1. And I'm just going to recall my formula. So if I enter it into my calculator, I'm going to have, I already have everything stored. So I'm going to have alpha y plus okay, and so that gives me 2.3. So this is equal to 2.3. So what is this? This is your new y coordinate. Okay, so what is my new point? This is going to be 1.1, because I'm going in increments of 1. I'm sorry, in increments of 0.1. And then my new y coordinate is 2.3. Okay, so that's my new point. Now I'm going to work with this. And this is going to be a point I'm going to use for the next one. Like so. Okay, so I'm going to apply this formula again. Okay, so I'm going to do f of 1.1 plus f prime of 1.1 plus, comma, 2.3, and times that by 0.1. Okay, and so I'm going to use this again, but I'm going to restore my y as 2.3, and I'm going to restore my x as 1.1.